Welcome to our talk, where we will be discussing the application of reinforcement learning to personalization and propose a way of simulating a wide range of synthetic personalization tasks, and also share some counterintuitive insights that we observe in our numerical experiments. So the most typical examples of personalization tasks include customization of website layout, contextual marketing, content recommendation, and behavioral nudging, or more generally, healthcare hyper-personalization. In terms of which approaches you can take, there are also many options, but the most notable ones are A/B testing, reference learning, recommender systems, or reinforcement learning. Now, for the purpose of this talk, we are mostly interested in addressing behavioral nudging problem with the methods from reinforcement learning. And to give you a very high-level overview, in behavioral nudging, we are given a patient who is typically described by the vector of demographic features. And we also have a set of actions in the form of messages that we can send to this client. And so the goal is to figure out what is the most appropriate message to send to the client, and send this message with the idea of bettering their overall health and behavior. So to formalize it, we will, for the purpose of talk, for simplicity, we'll consider the contextual bandit setting, which consists of the three main components: the continuous state space S, and this is really our vectors of demographic features of the observed clients; a discrete action space A, which really represents the set of available actions that we can communicate to patients; and a reward function that is represents a feedback that we would observe after we send an action, a message to a patient. An agent in this context would be any kind of system that takes as an input observed state, produces action, and then observes the reward, and typically adjusts its weights and learns on this interaction. So the overall problem is stated as follows: train an agent that for a given observed state selects an action that produces the height reward. So overall, it's very similar to a conventional contextual bandit problem. However, there's a lot of complexity in this problem once you account for the fact that we're talking about real-world healthcare applications and we are actually communicating with real people, and that suddenly makes everything much more complex. So the particular problematic points in this area are your agent environment interactions are typically restricted by something, be it either ethical, practical, security considerations, maybe legal, maybe cost considerations. We're not sure, but there are many restrictions. So that typically means that you generally have little data of interaction with your environment. On top of that, we have a notoriously complicated geometry of the reward signal, because it is indeed tied to human behavior and depends on some hidden behavioral features which are not known, and your agent essentially has to learn them. On top of that, even further, the whole learning objective is typically non-stationary. This is due to the fact that people's preferences may change over time. And since we are dealing with human-given feedback, humans, unfortunately, are not deterministic. And so the feedback we observe also is not deterministic, and that makes it very hard to learn. And just to complete this incomplete, unfortunately, list, there's not really a well-established set of benchmarks for this type of problems, and there's not a lot of public data sets for this type of personalization, and usually all the data sets are proprietary or you cannot use it in a research. So that definitely poses a lot of complications in addressing this kind of problems for reinforcement learning. So the proposals that we have, what definitely would be of a great advantage to this whole area, if there would be a framework for generating a synthetic personalization environments on which you can test different learning configurations to try to figure out what might work in your particular application and what will not work. And so this is, of course, an ambitious goal, but we will share our thoughts and our initial attempts on achieving that goal. So to that end, we will introduce a synthetic personalization environment that will consist of three components. First is a generator of observed states. Second is a state of available actions. And third is a reward function. And out of these three, by far, reward function is the most complicated thing to simulate, because even in real life on real data, we have no idea how this actual reward signal would look like. So simulated is indeed complex. However, there are some at least necessary conditions that we can impose on this function. And so those conditions specifically are the following. Reward values definitely have to depend on the latent features on both state and action side. And on the state side, it might represent the behavioral features that your agent has to learn. On the action side, it might represent the semantic meaning encoded in your message that the agent also has to learn and extract. And also, this overall mapping that you're creating must be sufficiently smooth if you want any kind of reasonable reinforcement learning system to be able to learn it. So how do we really go about creating such a system? For simplicity, in this talk, we propose the following concrete design that consists of 3 blocks. First is a state feature extractor that would take as the input observed state and find its feature representation in a latent feature space L. Second is an action feature extractor, which would do the same thing for an action. It will take an action and outputs the latent feature representation in a space L. And then finally, once I have the representations in my latent feature space L, I will use some kind of relevance function to determine how good this action for this state is. Relevance function and how you design it is completely up to you, and it's suitable, whatever is suitable for your application. In our case, we just consider inner product, and that's what we use in our tests. And so out of these 3 blocks, really the only problematic ones are state feature extractor and action feature extractor. Indeed, how do we set up such a mappings that can act as a abstract feature extractors? And this is where we introduce the concept of synthetic Gaussian mapping. And what that really is nothing more than a feed-forward neural network, but of a particular structure. So here's how would you construct one of them. So first, you select a favorite architecture, so a number of layers, number of neurons on each layer, and then you would initialize weights with from the normal distribution, with the only caveat here that sigma that we use is a relatively big number. So in our test, we use sigma value of 1. So we basically initialize weights from a standard normal distribution, and this is not a conventional approach. But then you would set your activations after each hidden layer to be Gaussian functions, or Gaussian activation function, which is also not a very conventional choice of activation. And finally, you would apply hyperbolic tangent activation to the output of your network to constrain the whole output to the interval -1, 1. And so we claim that if you consider mapping generated like this, you will have a function that can act as an abstract feature extractor. And here we will give a brief demonstration of our claim. So what we do on this slide, we generate a family of abstract mappings from a 2-dimensional unit cube into 9-dimensional space. And each of these mappings we generate with basically synthetic Gaussian mapping. And the results you can see on the screen. So specifically on the left, what you see is a coordinate-wise output for each of the 9 dimensions for each of these mappings. And on the right, you can see prediction, or more specifically activation patterns on a 2-dimensional input space. Now, what I want you to note is that these mappings, on one hand, look sufficiently random, but on the other hand, they look very intentional. There's definitely networks that do something, that extract some sort of abstract features. We, of course, have no way of knowing what those are, and more specifically, they are nothing because they're completely randomly generated. But these are the mappings that definitely extract some sort of features. And also what is very nice is that by controlling the architecture of synthetic Gaussian mapping, I can control how intricate those feature extractors are. But more specifically, using this approach, we can generate some kind of feature extractor to be used in our reward function, which in turn completes the construction of the synthetic personalization task. So now we can actually go and try to solve this task. So to take a slight step back, we come back to our problem. So we now have a synthetic problem, a synthetic environment, and we want to learn it. However, if you actually base it on a real data, you will quickly notice that there is a pretty big challenge in the form of dimensionality of your state space. Usually in practice, the dimensionality of your state space is excessively large. And by itself, this is not a bad thing, but it is a pretty bad thing in conjunction with the fact that your agent environment interactions are typically restricted. So you don't have that much data, and there's just not a lot of data to learn this high dimensional embedding. So surely there are ways around it. And one of the conventional ways of sort of artificially reducing dimensionality and or complexity of your problem is to consider some form of state abstraction. And which exact state abstraction you will implement depends greatly on which tools are available to you, how much information about your model you have. But either way, you can do state abstraction. You will simplify your learning task, but it comes at a slight price of some information loss about your overall environment. And whether or not to make this trade-off is up to you. But for the purpose of this talk, and in order to really highlight counterintuitive nature of our findings, we would consider the most naive, the most simple form of state abstraction, which is specifically state space clustering. And that is exactly what it sounds like. We will take a high-dimensional continuous state space, and we will cluster it based on well, in our case, Euclidean metric. And we will obtain a lower dimensional discrete state space that is easier to learn. But of course, by doing this clustering, you lose a lot of state parameterization information. So naturally, there's a lot of questions here. So more specifically, here's what we do. We consider two approaches. First is a full reinforcement learning approach, which is very conventional. You have environment, you deploy your agent on it, and you learn. And second is a state clustering approach. And that's where you have environment, but you first cluster it to obtain a low dimensional discrete state space S bar, and then you deploy your agent on this simplified environment S bar. And the logic here is that this environment should be easier to learn. And of course, that by itself brings a lot of questions. Most notably, is this a worthy trade-off? But more specifically, we're pursuing two questions. First, does the state space clustering actually accelerate the learning in the short term, to which you probably might think yes. And the second, does the state space clustering restrict the agent's learning in a long run, which again, I personally would say yes, because you lose a lot of information by doing space state clustering. So now, before going to our numerical results, two words on which metric we are reporting. And here, let's recall that the return of a policy is denoted as just expected reward under this policy. But then we also normalize, and we report the normalized return V tilde, which is denoted as return subtracted return of the uniform random agent and divided by return of the optimal policy. So why we report this metric? Because normalized return of a uniform random policy would be 0, and normalized return of the optimal policy would be 1, regardless of your actual reward function. And so that tells us that for any non-trivial policy, we would expect normalized return to be somewhere between 0 and 1, and preferably as close to 1 as possible. And this is the metric that we are reporting. Okay, so now talking about our numerical findings, let me walk you through this picture. So on the x-axis, we have number of time steps, or more specifically, number of unique agent environment interactions that go from 0 to 100,000. And on the y-axis, we have this normalized returns that we defined on the previous slide. So now what we do here is we consider three very popular algorithms for reinforcement learning. Those include advantage actor critic, deep Q network, and proximal policy optimization. And for each of the algorithms, we use two approaches. First is direct or full reinforcement learning approach. And second is we cluster the environment first and then use this simplified environment. And so the results are shown in this graph. And so from here, we can start answering those questions that we posed previously. So specifically, first question is that does state clustering accelerate the learning in the short term? And indeed, it seems to be accelerating. You can see that performance of the clustered agents increase faster. So no surprise here. But the second question is interesting, because the question was, does the state clustering limit the performance of your agent in the long run? And surprisingly, answer here is no, it does not. And not only on this example, we run many more tests in different configurations, and pretty much never we observed significantly worse performance on a clustered environment, which is very counterintuitive. But what's probably even more important is a third insight that we observed, is that in this and all other tests that we run, you can see that the Y scale is capped much lower than 1. If an agent would really learn the environment fully, I would expect this normalized score to be closer to 1. But we never see that on none of the tests. And so what that tells us is that these conventional algorithms that people use in reinforcement learning might not be expressive enough to capture this intricate structure of the reward signal in these complex personalization tasks. And even if you do state space clustering and lose a lot of information this way, it still doesn't really matter, because apparently the conventional full reinforcement learning approach is not capable of capturing this information in the first place. So to briefly summarize what we've talked about here. First of all, we briefly talk about reinforcement learning in personalization and outline some very prominent sources of complexity for real life reinforcement learning. Then we proposed the synthetic personalization environment and how to create them and how to test your algorithm on them. And then finally, we empirically observed that there seems to be a lack of a more of advanced enough reinforcement learning methods that can be used to consistently solve these complicated environments. And so what that really tells us is there's a dire need in developing more advanced techniques, whether it's in a form of policy architectures or different learning objectives or more sophisticated optimization algorithms, but something needs to be done so that this type of problems can be learned, simulated, and in practice. Okay, so with that, that concludes my talk. More details you can find in our paper. The code you can find is publicly available on GitHub. And we are looking forward to your questions during either live Q&A session or over email later. Let us know. We'd be happy to talk about you. And thank you for your attention.